latest report indicates that it became extremely bright, much more than expected for familiar comets.
What's unfolding right now with interstellar object Atlas and the concurrent explosion of solar activity represents genuinely one of the most remarkable astrophysical events observed in decades. This is something making veteran solar physicists sit up and take notice, something that has NASA scrambling to get every available telescope pointed in the right direction. Over the past several days, ATLAS has undergone a dramatic brightening event that has far exceeded the most optimistic projections.
It actually is bluer than the sun, and a blue color usually indicates very high temperatures if the light is emitted by some hot surface.
This isn't just a little bump in luminosity. The object has become multiple magnitudes brighter than what models predicted based on its composition, trajectory, and distance from the sun. And here's the absolutely fascinating part. This brightening has coincided almost perfectly with what is shaping up to be the most intense period of solar activity seen since the early 2000s. The scientific community is potentially witnessing Halloween Storms 2.0, except this time there's an interstellar visitor in the mix. Context is everything here. Atlas reached its perihelion, its closest approach to the sun, just yesterday on October 29th. The object came screaming in at a distance of only 1.36 astronomical units from our star. For reference, Earth sits at 1 astronomical unit, so this object was experiencing solar radiation levels of approximately 735 watts per square meter. Compare that to what it was receiving out in deep interstellar space, somewhere around 10 to the -7 or 10 to the -8 watts per square meter, and the absolutely massive energy bombardment this thing is undergoing becomes clear. But here's where things get really wild. During its close approach, Atlas didn't just get hit with normal solar radiation. Instead, it got absolutely pummeled by some of the largest coronal mass ejections observed in years. These weren't garden variety CMEs. These were monsters, massive explosions of magnetized plasma erupting from the far side of the sun with incredible force and energy. Events that, if they had been Earth-facing, would have had emergency management agencies around the world on high alert. The timing of all this is what really excites from a scientific perspective, because this has been tracked for months. Back in July, when analysts first started examining the trajectory of ATLAS and comparing it with historical solar cycle data, forecasts indicated there was a significant probability of enhanced solar activity coinciding with its perihelion passage. Many were skeptical. The question arose, how could a passing object influence solar behavior? But the data doesn't lie, and what's being observed now is exactly the scenario outlined months ago. The solar story here is almost as compelling as the interstellar object itself. For the past 10 days, the far side of the sun has been absolutely erupting with activity. Massive sunspot groups, complex magnetic structures that are breeding grounds for explosive events, have emerged. These aren't typical sunspots either. The helioseismic data shows structures that rival some of the largest and most complex sunspot regions ever observed. And here's the crucial point. All of this activity has been happening on the far side of the sun, the side that can't be directly observed from Earth. But observers aren't flying blind. Thanks to coronagraph imagery from SOHO, the C2 and C3 instruments specifically, these massive CMEs launching off the solar surface have been watched in real time. Multiple coronal mass ejections, each one more impressive than the last, blasting outward into space, and sitting right in the path of several of these eruptions was Atlas. The first major CME occurred on October 21st, right as Atlas was in superior conjunction with Earth. That means there was an alignment of Earth, Sun, and ATLAS all in a row. And boom, a massive coronal mass ejection launched directly in the path of the interstellar object. Since then, there have been at least 5 or 6 more major events, with the most recent ones occurring just in the past 48 hours. These CMEs are carrying enormous amounts of energy, plasma, and magnetic field structures, and they're slamming into 3I/ATLAS like a cosmic fire hose. Now, what this bombardment is doing to the interstellar visitor is where things get really fascinating. Thanks to the work of researchers like Chi-Cheng Zheng and Carl Battams, who just released a preprint analysis using available coronagraph imagery, the best look yet at how 3I/ATLAS is responding to this extreme environment is available. And the results are stunning. The object has brightened dramatically, far more than would be expected from a typical solar system comet at this distance. The light curves published show that 3I/ATLAS has reached an apparent magnitude around 7.5 to 9, depending on how the data is normalized, whereas models predicted it would be several magnitudes dimmer. This is a huge discrepancy, and it's revealing that something very interesting is happening with this object's composition and structure. What's being observed is consistent with massive outgassing, the release of volatile materials from the nucleus as it's heated and bombarded by solar radiation and plasma. But here's what's different from normal comets. The spectroscopic signatures show unusual abundances of certain elements and compounds. There's a lot of carbon dioxide, a lot of water ice, but the ratios are different from what's seen in Oort cloud comets. There's also an unusually high concentration of nickel, but relatively low amounts of iron, which is backwards from most solar system objects. This compositional weirdness might explain why 3I/ATLAS is responding so dramatically to the solar environment. Different materials have different sublimation rates and different electrical properties. When that's combined with the extreme conditions being experienced, enhanced solar radiation, direct impacts from coronal mass ejections, immersion in dense solar wind streams, the result is an object that's essentially being lit up like a Christmas tree. The coronal mass ejection impacts deserve particular attention because people often underestimate just how violent and energetic these events are. When a CME slams into a planetary magnetosphere, or, in this case, the coma and nucleus of a comet or interstellar object, a massive electrical interaction is essentially created. Current sheets form, magnetic field lines reconnect, and enormous amounts of energy get dumped into the system in a very short period of time. Think about what happens on Earth when a big CME hits. Aurora dance across the sky from the Arctic Circle down to mid-latitudes, sometimes even reaching places like Hawaii or the Caribbean if the storm is strong enough. That's the visible manifestation of electrical currents flowing through the upper atmosphere, exciting atoms and molecules, causing them to emit light. Well, the same basic physics applies to 3I/ATLAS. When those CMEs hit, they're driving electrical currents through the object's coma, heating material, stripping electrons from atoms, creating a glowing plasma sheath that makes the object appear much brighter than it would from solar radiation alone. Now, attention needs to shift back to the solar activity itself because there's a critical development approaching. Those massive sunspot groups that have been so active on the far side are rotating towards Earth. In just 2 to 3 days, the leading edge of these regions will start appearing around the solar limb. Within a week, they'll be center disk, pointed directly at Earth. And if they maintain anything close to their current level of activity, a major space weather event could be imminent. The Halloween storms of 2003 keep coming to mind because the parallels are really striking. Back then, there was a similar situation, a massive complex of sunspots rotating into view, followed by weeks of intense solar activity. Multiple X-class flares were observed, some of them double-digit X-class, which are extremely rare. Back-to-back coronal mass ejections hammered Earth's magnetosphere, causing severe to extreme geomagnetic storms. Aurora were visible from places that hadn't seen them in decades. There were disruptions to power grids, satellite operations, and communication systems. And here's the really interesting parallel. During the Halloween storms, the planet Mercury was in superior conjunction with the Sun, meaning it was on the far side aligned with Earth and the Sun. Mercury has a magnetic field, one of only 2 rocky planets in our solar system with an intrinsic field, the other being Earth. There's been speculation for years that these planetary magnetic fields, when aligned through the Sun, can influence solar activity by affecting the electromagnetic dynamics of the heliosphere. Solar physics is complex, and there are many factors that influence whether a sunspot region produces major flares and CMEs. But the correlations seen between planetary alignments, particularly those involving magnetic fields and enhanced solar activity, are statistically significant. And that's exactly the framework that was being used back in July, when forecasts indicated that ATLAS's perihelion passage could coincide with elevated solar activity. Atlas is essentially a giant ball of rock, ice, and plasma flying through the inner solar system. It has electrical properties, it has mass, and it's interacting with the sun's magnetic field and the solar wind in complex ways. And when it aligned with Earth and the sun on October 21st, the first major CME launched. Since then, the activity has only ramped up. Coincidence? Maybe, but the timing is remarkably precise. The helioseismic data from the far side shows that these sunspot groups are not calming down. In fact, they appear to be growing and fragmenting, which often precedes major eruptive events. One of the primary groups has expanded significantly over the past week, spreading across a wide swath of the solar surface. Now, there needs to be a caveat here. Helioseismic imaging is low resolution. Sound waves propagating through the sun are being used to infer what's happening on the far side, so there's always some uncertainty. But the signatures being observed are consistent with very large, very complex active regions. What's particularly concerning or exciting, depending on perspective, is that the CME rate isn't decreasing. Just in the past 48 hours, there have been 2 more major eruptions from these groups. If that trend continues as they rotate into Earth view, a sustained period of severe space weather could be approaching, and the implications for ground-based infrastructure need to be considered. Geomagnetic storms at the G4 or G5 level, severe to extreme on the scale, can cause real problems for modern technological infrastructure. Induced currents in power grids can damage transformers, the kind of damage that takes weeks or months to repair. Satellite disruptions can occur, both from direct radiation damage and from atmospheric drag caused by the upper atmosphere heating and expanding during storms. GPS signals can be degraded or completely lost. Radio communications, particularly high-frequency systems, can be blacked out for hours or days. This isn't fear-mongering. The vast majority of geomagnetic storms, even strong ones, don't cause catastrophic problems. Infrastructure is better protected than it was decades ago, and early warning systems provide time to take protective measures. But the potential exists, especially if multiple CMEs hit in quick succession, which is exactly what happened during the Halloween storms, and exactly what might be approaching now. And there's another factor to consider: the timing with the lunar cycle. A full supermoon is coming up on November 5th. The moon will be at perigee, its closest approach to Earth, sitting at about 356,000 kilometers. That means stronger tidal forces, not just on the oceans, but on the solid Earth itself, and potentially on the magnetosphere. The moon passes through Earth's magnetotail during the full moon phase, interacting with the plasmasphere and potentially enhancing geomagnetic disturbances. Combine that with active solar conditions, and there's a recipe for elevated seismic and volcanic activity, as well as enhanced space weather effects. Speaking of seismic activity, an earthquake watch period is currently active. A high-speed solar wind stream from a long-lived coronal hole is impacting Earth, and a G1 geomagnetic storm is in progress. Historical data shows a strong correlation between specific solar wind conditions, particularly when the particle density drops below 1 particle per cubic centimeter, and major earthquake events. The working hypothesis is that these density variations create pressure fluctuations in the magnetosphere that can trigger stress release in tectonically active regions. It's controversial, but the statistical correlations exist. Right now, geomagnetic fluctuations are being observed primarily at high latitudes, around the Arctic and Antarctic circles, but there's elevated activity at mid and even equatorial latitudes. The magnetic field measurements are showing variations up to 400 nanoteslas and beyond, which is consistent with minor storm conditions. If this escalates to severe or extreme levels with the incoming sunspot groups, magnetic field swings an order of magnitude larger could occur. For aurora chasers, this is potentially shaping up to be an incredible period. If G4 or G5 storms develop, aurora could be visible from locations that almost never see them, places like the southern United States, the Mediterranean, northern Australia. The displays could be spectacular, with multiple colors, rapid movement, and unusual forms. But for those thinking about infrastructure resilience and societal impacts, it's more concerning. Now, Atlas shouldn't be lost in all this discussion about solar activity because there's an incredible scientific opportunity unfolding. This object is going to continue moving away from the Sun now, heading outward past Mars toward Jupiter's orbit. Direct visibility will be lost for a while as it moves through the bright glare of the Sun as seen from Earth. But starting in mid to late November, ground-based telescopes should be able to pick it up again. The ESA's JUICE mission, which is currently in the inner solar system on its way to Jupiter, should be able to get some observations starting around November 2nd. That could provide valuable data on ATLAS's appearance and behavior after perihelion. But for the most part, reliance will be on advanced imaging techniques, long exposure photographs, and careful image stacking to extract signal from noise. This point deserves emphasis because as soon as ATLAS becomes visible again, there's going to be a flood of images circulating on social media, and not all of them are going to be processed properly. A telescope can't just be pointed at this thing with expectations of seeing it clearly in a single frame. Multiple long exposures are needed, careful alignment, and sophisticated stacking algorithms to bring out the details. So when images appear online, they should be taken with a grain of salt, unless they're coming from reputable sources with documented methodology. The latest positional data from NASA JPL shows that ATLAS is right on track with its predicted trajectory. There's been no deviation, no anomalous acceleration, nothing that would suggest anything other than a passive object following orbital mechanics. That's important because there was speculation early on about whether this might be something artificial, given its interstellar origin and unusual characteristics. But everything being observed is consistent with a natural object, albeit one with some strange properties. The fact that it has brightened so dramatically reveals information about its composition and structure. The lack of a prominent tail, unlike most comets, suggests either a different dust size distribution or a different outgassing pattern. The spectroscopic anomalies hint at a formation environment different from our solar system's Oort cloud. All of this is valuable data for understanding planetary system formation, cometary science, and the diversity of objects in the galaxy. What's absolutely fascinating is how this event is tying together multiple scientific disciplines: solar physics, cometary science, space weather forecasting, magnetospheric dynamics, and even seismology are all intersecting in this one remarkable period. It's a reminder of how interconnected everything in our cosmic neighborhood really is. The sun doesn't just sit there passively radiating light. It's a dynamic, variable star that influences every corner of the solar system. And when something unusual comes flying through, like an interstellar visitor, it adds an extra layer of complexity to an already intricate system. Looking ahead to the next week or two, here's what bears watching. First, how these sunspot groups look when they rotate fully into view. Are they as large and complex as the helioseismic data suggests? Are they still actively flaring and producing CMEs? Second, the first Earth-directed CME from these regions. When that happens, there will be about 15 to 24 hours of warning before it impacts the magnetosphere. And that's when determination can be made whether this really does shape up to be a major space weather event. Third, monitoring of ATLAS to see if its brightening continues, plateaus, or starts to decline as it moves away from perihelion. The rate of change will reveal a lot about what's driving the enhanced luminosity and how the object is responding to decreasing solar input. And finally, keeping an eye on seismic and volcanic activity globally to see if any upticks correlate with the geomagnetic disturbances. For those concerned about potential impacts on daily life, the advice is standard. It's good to be prepared regardless of what the sun is doing. Basic emergency supplies should be on hand, enough food and water for 72 to 96 hours. A hand crank radio is valuable for staying informed if power goes out. Those in regions prone to aurora should keep cameras ready because a once-in-a-decade photo opportunity might be approaching. But more than anything, the incredible scientific spectacle unfolding deserves appreciation. Events like this, where multiple extraordinary phenomena converge, don't come around often. The last really comparable situation was over 20 years ago. There's a front-row seat available to the dynamic, violent, beautiful nature of our star and our solar system's interaction with the wider galaxy. That's something special. This is what makes space weather and planetary science compelling. It's not just abstract numbers and equations. It's real, dynamic, and it directly affects life on our pale blue dot. As one of the most remarkable astrophysical events in decades continues to unfold, the opportunity exists to witness something truly extraordinary. Stay informed, stay prepared, and keep watching the skies.